So today is Friday, September 11th. Oh my goodness, this is kind of a Memorial kind of a day. But it's not Memorial Day. Okay, but yes, it's September 11th. And I actually taught on September 11th, 2001. I was teaching a very large class. It was quite a sad time. But anyway, and this is 641 model-based imaging or digital image processing 2 or whatever it's called. And today we're going to finish up the material on causal Gaussian models, and we're going to do the 2D case, okay? And so the idea in a causal Gaussian model is that you basically you have okay, you want to write down the probability distribution of the complete sequence, okay? So one way of doing that is that you write down, see, xn times xk for k less than n times p of xn minus 1 given xk for n minus 1. And you keep going all the way till you get to p1. And actually, P1 doesn't have any conditioner on it, okay? So you can always do this. You can always write a I know this isn't what is in the book, but I'm giving you a different perspective on this. So you can always do this thing. This thing's really annoying. I don't know why you can't do something with it, okay? You can always write down the probability distribution of x as the probability of each of the of each step. See, that's the intuition, right? So you have a sequence. It's important to have some intuition. Oh, I promise I don't have coronavirus. So it's important to have intuition and then to also be able to write the equations down that represent that intuition. Alessandro, can you just double check to make sure the microphone thing is going up and down?
Yeah, you're good.
Okay, good. So the intuition is, these are the equations, but the intuition is this, that if you want to ask for the probability of the sequence, you can ask for the probability of each new step in the sequence, okay? It's like you start off by saying this is x1, say what's the probability of x1? Then what's the probability of x2 given x1? Then what's the probability of x3 given x1 and x2, right? That's called a Markov chain. Well, if it's discrete state, it's called a Markov chain. If it's continuous state, it's called a Markov process. Actually, no, that's not. I forget. Markov process is continuous time. It's called a Markov chain, okay? So, fine. This is a simple Markov chain. It's a simple case because the values are Gaussian, so it's easier to do calculations. So the way that exhibits itself in our problem is that we can write down the probability. Well, first of all, what ends up happening is that epsilon n is equal to xn minus x hat n. So in vector notation or matrix notation, that becomes epsilon equals, oh, I had the equations wrong last time. It was I minus h. Is that how I did it? I should have done it, times x. And that's equal to a times x. Okay? And a here looks like it has 1s on the diagonal because the 1s represent the fact that you're just using your current value. This is xn. So this is x hat n, and this is epsilon n, okay? All right? So that's the prediction error. It turns out that these prediction errors are all white, okay? Because why is that true? Whenever a student asks me something like, why is that true? you know, questions like that really don't have any answer, okay? Because the only answer is because you do the calculation and it comes out that way, okay? But somehow that doesn't really satisfy you. It shouldn't satisfy you, okay? Because it doesn't impart any understanding. The problem is that the word understanding has no definition as far as I'm aware. It's something that you know intuitively, but really can't define. I mean, what does it mean to be able to understand something, right? I mean, honestly, if I was going to retire, there would be a few things I would spend my time probably I'd end up like building model airplanes instead. But I might spend my time, theoretically, I'd like to spend my time trying to understand things like understanding, okay? Because it's a very subtle mathematical concept, okay? But, so you'd like to impart some understanding, okay? So, I don't know exactly how to do that, but I can give you some intuition, okay? So the intuition is that each new prediction error, right, is sort of what's left when you squeeze out all the past. So it's only the new stuff, okay? You squeezed out all the past information, and you only have the new information. So therefore, each new piece of information is independent of all the past. So that means that each of the prediction errors must be independent of each other. And since they're Gaussian, that means they're uncorrelated. So it turns out that the expected value of epsilon times epsilon transpose is equal to sigma squared I, assuming that the random process is stationary. Okay, I'm lying a little bit because I'm modifying the definition of stationary, because stationary has to go to infinity. But if the prediction variances are invariant, so this would be what they call a homogeneous Markov chain. Okay, then this is going to be the same for, it could, more generally, it could be that the prediction variance for each component was different, but a function of time, in which case this would be a diagonal matrix, but not necessarily proportional to the identity, okay? Now, okay, fine, but the other important thing is that the determinant of A equals 1. Because the determinant of A equals 1, it turns out that it's much easier to write down the probability distribution. And it turns out it's P of x is equal to the exponential of minus 1 over 2 sigma squared. This is x minus AI. X minus A, oh, no, I'm sorry. It's equal to AX transpose AX, right? And this is 1 over z. So this thing here is going to be 1 over z times the exponential of minus 1 over 2 sigma squared x transpose A transpose AX. So this thing here, B is equal to A transpose A. B is the precision matrix. Okay? R is equal to B inverse, which would be the covariance matrix of X. We'll call it Rx, okay? So that's the covariance matrix, okay? And, okay, so that's kind of cool, okay? And going back, remember, A here is equal to I minus H, where H is the prediction filter, okay? So that's all good, and you can work some of those problems. In 1D, this is terrific, okay? It's terrific because it turns out that you can take any, okay, this R is a positive definite matrix. It's a positive definite matrix. It's a symmetric positive definite matrix. Any symmetric positive definite matrix is a legitimate covariance matrix, okay? So if I take its inverse, it's also going to be a symmetric. It's got to be positive definite too. Why? Let me do a quick proof of that. Do people believe that? Or is it obvious? Okay, I don't think it's obvious. Quick proof. So if R is equal to E lambda E transpose, right? Okay? So B is equal to R inverse. The inverse, it's easy to show, is E lambda inverse E transpose. Do you want me to prove that? It's super easy, because what I do is I just multiply R inverse by R, right? E transpose times E is identity because it's an orthonormal matrix. So E transpose is the inverse. By the way, electrical engineers, pretty much to a person, all subliminally believe that every matrix's transpose is its inverse. Okay? It's not true. It's important to be aware of this belief you have so you can try to squelch it. Okay? And the reason you believe this is because in everything you've ever been taught, you've always dealt with orthonormal matrices. So when you took the transpose, they were always the inverse, okay? But it's not generally true. For an arbitrary matrix, you know, it's not true, right? I mean, orthonormal matrices are very particular. So for the FFT, when you take the FFT, take the inverse FFT, you just multiply by the transpose, the conjugate transpose. That works because it's an orthonormal matrix. But for an arbitrary matrix, it doesn't work. If you have a communications or radar background, which I guess fewer people do these days, you don't have a question, do you? No, okay, that's fine. I don't mean to disturb you. I just wanted to check that you didn't have a question. If you have a radar or a communications background, when there's this thing called a match filter. How many people have heard of a match filter? Okay, good. So a match filter is the transpose operator. And the assumption is that, you send the signal out, and then to decode it, you use the match filter, right? So there's sort of a sense that it's the inverse, but it's not the inverse. It's just the match filter. So the idea is that for a randomish matrix, A transpose times A tends to be approximate a scaled identity, okay? But not really. So that means that a lot of applications, and what will happen in the physical sciences, people often think that the way you can invert a system is by multiplying by its transpose. They think that, and often you'll read, to even make things more complicated or more confusing, there's a lot of theorems that state that that's the optimal decoder, okay? It's optimal in some certain senses, but there's also a lot of things that they do in these fields that they kind of reverse engineer. They find some criteria which is optimal for the thing they wanted to do. And then they use it as sort of a circular justification, okay? It's useful because sometimes it's nice to know like some justifications for the things you're doing. But you were doing them anyway, okay? It turns out, but it's not. So in a lot of this class, a lot of what this class is about is that in the classic processing, you tend to do that. You want to invert a signal, you just multiply by A transpose, and that gives you sort of a rough inverse. But it's really bad, okay? So then the next thing you'd say is, well, I'll do multiply by A inverse. But that's not practical because usually it blows up because you'll have eigenvalues that are too small or single values that are too small. So this class is all about finding about inverting things like that, okay? I just like to insert those things every once in a while because every once in a while you kind of lose track of why we're even here, okay? So we know this, okay? So the point is that this thing, the elements of this thing are also greater than 0, right? Because if you take a positive number, you take the inverse of a positive number, you get a positive number. So my point here is that B is a positive definite matrix. B is a positive definite matrix. Okay, and so if you take any positive definite matrix, it's a legitimate precision matrix. Okay, and then and that's what it is. Okay, so that's good. Okay, so that was a quick review. Now, any questions about any of that? Okay, then I want to go on to the 2D case. So now, so 1D, I know what my point was here. If I take any positive matrix, a positive definite B, a matrix B, it turns out I can always factor it into an upper triangular and a lower triangular part, okay? So I can always find a matrix, I guess what'll happen, okay. So this would be like a lower triangular, and at 0 like that. And then I guess this would be an upper triangular. I can always find a matrix A. I think that's called the Cholesky factorization. I should know this. Does anybody know what the name of that is? It's a standard numerical thing to do, okay?
LU decomposition, I think.
What's it called?
LU decomposition is something that you can write any matrix as L into U.
Oh, LU, right. Maybe it's the LU. Okay, that's called the LU that's what it's called.
Special case of this because matrices.
Yeah, okay. The point is you can do it, okay? So the point is this. You give me any 1D random process, any 1D Gaussian random process, I can represent it this way. It's completely general in 1D. Now we have to go to 2D. It's going to turn out in 2D it's not completely general, okay? It's not completely general. Yeah, the concept of generality here is a little bit subtle, but you're going to read the notes too, right? So 2D. In 2D, if you want to do this in 2D, you've got to have a causal representation of the data, right? So you have something like this. These are the points in 2D. So you want to predict that point right there. So the question is, what is the past? What's the past, okay? In 1D, the concept of the past is, reasonably clear. The only thing that is a little bit unclear about the concept of the past is you have to figure out which direction time is going in, okay? So is time going this way or is it going that way? It turns out, this is something else I wanted to say. Gaussian random processes are always reversible. I forgot to define reversibility. I talked about it. So you're going to read the notes, right? And the notes define reversibility. Reversibility is just like stationarity. The difference, stationarity says that if you take a window and you move the window, the distribution of the samples in that window are invariant to the position of the window, okay? Okay. The values aren't obviously independent, but the distribution is independent, okay? And stationary in 2D, okay, we talked about that. That was on the pizza. In the reversibility means if I take the random process and I flip it in time, if I take a stationary random process and I flip it in time, its distribution remains the same. That's not always the case. So, and there's a problem where you're supposed to give a counterexample to reversibility, right? Do you have that was there a homework problem you did where you have to provide a counterexample to reversibility? You have to find a non-reversible Gaussian random process. Yes, no, do you remember? Did you? Excuse me?
Something just stationary but irreversible.
You said, did I ask you to find something that was not to stationary but not reversible? Is that correct? Yeah, okay. I'm having a little trouble. Honestly, one thing that's kind of interesting, it's a little difficult to understand people when you can't see their lips move. So, yeah, I apologize if I have to ask you to repeat yourself. So, an example is this. If I let's say I have, everybody knows what a linear time invariant system is, right? So I take H here, and that's Y. So Yn is equal to Hn convolved with Xn, right? And this is Xn, right? Okay, so So that's what that is, okay? So it's linear time invariant. Now, what if xn, let's take a particular case. Oh, let me do it. Okay. I'm going to get a particular linear time invariant system. So this is z to the minus 1, okay? This is plus, plus, and this is a, okay? Where say a is equal to 0.9, okay? So then yn. So the impulse response of this system, h of n, is equal to u of n times a to the n, okay? Right? Does everybody know that, or does that look kind of familiar? The impulse response of the system looks like this. Okay, so let's see. Oh, everybody knows what an impulse is? And do you know what an impulse response is? Okay. So you have an impulse, you'll get an output of 1 at time 0, right? And then at time 1, what will you get as an output? Alessandro, do you know what an impulse response is? Because this is like electrical engineering speak. So, but you're not sure. That's okay. Excuse me?
I was paying attention to a different part.
Oh, okay, I'm just checking because I hope you don't mind, but you're my sample student for a non-electrical engineering student.
I did not learn of impulse response in my materials engineering background.
Okay. Let me tell you then, because it's a very important concept. So this is a system, call it T. Okay, right? The impulse response of a system is like if you put in an impulse, okay? So and the output is called H, okay? That's the impulse response. So if you put an impulse here is equal to 1 if n is equal to 0, and it's equal to 0 if n is not equal to 0, okay? Okay? Do you know what a Green's function, I bet, right? A little bit, okay? That's also kind of an electrical engineering concept because it really comes from electromagnetics. It's the analogous, Green's function is sort of a generalization of an impulse response for a space-varying system. But anyway, so this is called impulse response. And the classic result is that you can compute, for a linear time invariant system, you can calculate the output as the input convolved with the impulse response, okay? All right, now, okay. And so let's imagine we put an impulse in here. You know what this flow diagram means, right? It means that, okay, this z to the minus 1 is a delay of 1 step. Okay, it's discrete time. So if I put an impulse in, the impulse immediately comes out, so I get a 1 at time 0. Then it gets delayed, multiplied by 0.9, and added back in. So at the first time step, the value I get out is what? Excuse me? It's going to be 0.9, or I'll just call it A, if that's all right with you, okay? Right? And then the second time step, the output I get is what? A squared. This is A squared, right? And then, so I get an exponentially decreasing, this is A cubed. So the impulse response is A to the n, okay? But it's not A to the n for negative values of n. This thing is a step function, which is equal to 1 for n greater than or equal to 0, and 0 for n less than 0, right? Okay? So this is the impulse response, okay? This is called an IIR filter, infinite impulse response. It's kind of a silly name, really. It should be just called a recursive filter, but it's not my fault, right? It's like they made that name up. It's like arguing with Purdue administrators. It's a waste of time, okay? So, fine. Okay, so you're good with this, right? Now, okay, what was my point? Oh, here, let's say that x, example 1, right? Let's say x n is I IID. What does IID mean? Independent, identically distributed. And the probability that xn equals 0, okay, is equal to 1 minus epsilon. The probability that xn equals 1 is equal to epsilon. Epsilon is a small number, okay? Intuitively, what does this mean? Explain to me in words what this random process, xn, what its behavior is. Well, okay, it's stationary, first of all. It's stationary because it's IID, right? So therefore, every time window looks the same as every time window, right? Okay, what values does the random process take on? 0 and 1, right? So what does it look like? Like, what does a sequence xn look like? What does a typical sequence xn look like? What does a typical sequence look like? Yeah, it's a sequence of 1s and 0s, but let's say epsilon is equal to 0.00001, okay? What's it going to look like? It's mostly a sequence of zeros. It's a very boring random process. It's like this, okay? And then what happens every once in a while? Every once in a while, it's like, whoop, huh. Okay? That happens every once in a great while, right? Okay. Now imagine that we put this random process, okay, into that filter. What's it going to look like? Yeah, I like that. That's the correct answer. You know what I mean? It's sort of like surfing or something. I don't know. Huh?
Get at the K starting at where it spiked.
So what'll happen is at this point, you'll get like the impulse response, right? And what'll happen here? It'll be zeros, right? So every once in a while, you'll get a little blip. Okay? This is a random process, isn't it? Is this a stationary random process? It is a stationary random process because if you put a stationary random process, X is a stationary random process. You told me that already. If you put a stationary random process into a time invariant system, doesn't even have to be linear, just time invariant, then the random process that comes out has to be stationary. Okay? Just intuitively, but you can prove it because if everything, you know, in physics, you got to give them credit. The physicists, or at least when I was young, I don't know how they teach courses now, they like to talk about symmetries and invariances, right? Symmetries are really invariances. So they talk about by symmetry, they'd say, it has to be true, okay? It makes a very short proof. It's not, I mean, it's better to fill in details, okay? But by symmetry, this has got to be stationary, correct? Is this reversible? Is this a reversible random process? So here's the question. If I reverse this random process, can you tell the difference? Does it look like the same? Could you tell whether this is playing backwards or forward in time? How can you tell? You just look at this thing and you see, well, hold on, it's obviously not symmetric. So yeah, you say, well, hold on, I could have like some probability of things coming up. But look, the probability of that happening is very small. I might tunnel through the wall, okay, but it's not going to happen very often. So this is, with high probability, you can determine that this thing is playing forward in time, not backward. Actually, with probability 1, because given that this thing was constrained, I don't think you could generate this output. If I made it Gaussian, maybe you could say, well, the very extraordinarily small probability. So this is not reversible, okay? However, example 2, if xn is IID and xn's distribution is n0 sigma squared, okay? Okay, n0 sigma squared. It's Gaussian. So it's a Gaussian. In this case, what's the mean of this random process? Is this process stationary? Is this a stationary random process? Okay. What's its autocorrelation? What's the autocorrelation function for this random process? So that would be the expected value. It's zero mean, so I don't have to worry about subtracting off the means, right? So I get xn times xm is equal to r of n minus m, right? Okay. So it's going to be equal to what? When m and n are not equal, what's the expected value? Is 0. By the way, I can prove that because if m is not equal to n, so if n is not equal to m, then that expected value, if I have independent random variables, I can take the expected value of the product is the product of the expectation. Not always true, but it's true when they're independent, okay? So then I get the expected value of n times expected value of xm. But these are both 0, so it's 0 times 0, which is equal to 0, okay? So this is going to be equal to 0 if n is not equal to m. And what's it equal to if n equals m? So it's sigma squared if n equals m. So there's a simple way of writing this. I can write sigma squared times delta of n minus m, right? So that's the autocorrelation. I know it's got to be a delta function, the autocorrelation, because they're independent. Okay. What's the power spectrum of that random process? We didn't talk about power spectrum, but you should have read the notes. How do you calculate the power spectrum of this random process? It's in the notes, right? It's a Fourier transform of the autocorrelation. So what's the Fourier transform of this autocorrelation? It's sigma squared. So it's flat. So the power spectrum, S of omega, between 0 and pi, okay? It's always going to be symmetric because it's a real valued function. Is what? It's just constant with value sigma squared. That's called white noise, okay? We'll find out. Oh, no, we won't find out because the class is 637. It's the reason we call it white noise is because the color white, okay, is approximately constant power spectrum as a function of wavelength, which is a little bit weird in a number of ways. First of all, it's wavelength rather than frequency. Second of all, it really isn't constant. Like if you take any real white, it's not very constant, okay? But whatever, it's kind of close enough, okay? So there's also things called pink and blue noise, okay? Pink would mean that if the noise was skewed towards the low frequencies. And blue noise would be, okay, blue noise doesn't exist in analog, but it exists in digital, okay? Blue noise you can't have in analog because we require that you have infinite energy because you have the spectrum which is high pass. That means it has energy that goes up to infinite frequency. It never happens. And the reason it doesn't happen, by the way, is because if you do statistical thermodynamics, you have to make assumptions about quantization of energy, which occurs due to quantum mechanics. So therefore, you don't get like infinite energy emission from a black body. But in discrete time, you can get blue noise because you're limited by a maximum frequency of pi. Okay, so all this, okay, so if it's Gaussian, it's IID. Okay, right. You put it in here, and then what comes out is a Gaussian random process. If you apply a linear time invariant filter to a Gaussian random process, what comes out in this case is a stationary Gaussian random process, okay? The stationary Gaussian random process is completely characterized by its autocorrelation. So the autocorrelation, the expected value of yn, I'm kind of going through all this stuff real fast. That's the autocorrelation for y. So we'll call that R of n minus m. The autocorrelation for y is equal to, is going to be sigma squared times h of n convolved with h of minus n, it turns out. Just believe me. If you convolve a signal with its time reverse, that's equivalent to doing correlation. So if this is the signal, okay, if you correlate, you just take the signal and you slide it. We're going to talk about correlation a lot in this class, actually, so I may as well talk about it right now. You slide it like this, okay? And the inner product you get as you slide the two across each other is the correlation, okay? It's the autocorrelation is the signal with itself. And in general, that's always a symmetric function, right? Because it doesn't matter if assuming my hands were symmetric, it wouldn't matter if I shifted them this way or if I shifted them that way. I get the same correlation, okay? Okay, fine. I'm like covering a whole bunch of like quick ideas that we're going to use. You have to get used to these things. It's like little building blocks, Legos that we're going to use to do things. So you got to get quick at them because you know. So, okay, here's the upshot. The output of this random process is stationary. Furthermore, it's reversible. Every Gaussian random process is reversible. Every Gaussian random process, every stationary Gaussian random process is reversible. Why? Because if I take a Gaussian random process and I reverse it, its autocorrelation remains the same. So the if I take z equals y, zn equals y minus n, I reverse it in time, it still has the same autocorrelation, because what will end up happening is I'll just basically for the same reason that this is symmetric, okay? If I have a thing in time, if I have a signal in time, if I look at the correlation between this point and this point, it's the same as the correlation between this point and this point. It doesn't matter. Okay? So if I reverse the thing in time, it has the same correlation. But a Gaussian random process is completely specified by two things. Its mean and its a stationary Gaussian random process is completely specified by two things. Its mean and autocorrelation. If I know let's just say its mean is 0, because that's simple. If I know its autocorrelation, I can write the distribution down for any segment of the random process. If I can write the distribution down for any segment of the random process, then I know the distribution of the random process. Okay? So basically, if I take a Gaussian random process and I reverse it, its distribution remains the same. Is the random process the same? No. Okay, because obviously, if I take some random process, it does something, I reverse it in time, it's different, right? But it's the same distribution. That's why you got to make a distinction between the value of a random variable and the distribution of a random variable. It's a critically important distinction which people don't understand. And this is why probability is abstract for people, and why you guys should be happy you're taking this class, because even though there's only a few people in here, the people who learn this stuff will be much more valuable when they leave here. And there will be companies and organizations that will want to hire you, because you understand random processes of probability and most people don't, okay? So the upshot is every Gaussian random process is reversible. The first example I gave you, that's not reversible, but it's not a Gaussian random process. Are regular single, okay, is speech reversible? Well, is it a reversible Gaussian random process? Is it a reversible random process? The answer is no, it's definitely not a reversible random process because it's not a random process. Because it's not like, that's the basic thing, that pizzas are not random variables, okay? It's not a random variable, it's not a random process, but we just model it as a random process, right? But then the question is it reasonable to model a speech as a reversible random process? Is it reasonable to model? It's a philosophical question. Is it reasonable to model speech as a reversible random process? Any thoughts? By the way, your answer can't be right or wrong, so you don't have to worry, because there's no answer to this question, right? It's a purely philosophical question. It's not precisely posed enough to have a yes or no answer. Yeah.
There are some consonants which you can model as white noise followed by some filter.
Right.
So that fits into this reversible Gaussian.
Yeah, like for example, like some phonemes. The classic phoneme is S. S can be modeled as white noise into a filter. S is probably well modeled as a reversible. The phoneme S is probably well modeled as a reversible random process. Go on. I cut you off, but what you said was so beautiful, I wanted to emphasize it, okay?
But if you take like a small piece of it may be reversible, but if you just piece it all together, it's obviously not reversible.
Like for example, let's say B, ba. Is that reversible? Model, well, you could do it. I mean, it might work great for whatever you're doing in your particular application, but clearly it has aspects to it that are not accurately modeled as reversible. Because it turns out for many phonemes, the way they model them is as impulsive noise, as impulsive signals, much like this, because actually usually periodic impulsive signals generated by the vocal cords, and that resonate through your vocal tract, and then they get filtered by something that looks like this, more or less, where it's mostly less. Okay, very approximately. Okay, so there. So now you know all about reversible random processes. Okay. Now, oh my gosh, we're running out of time. I got carried away. Okay, so I wanted to do this. I don't know. Oh, it's fun. Okay, now 2D. You're going to have to read this, okay, because you have, okay, they come back to this question of, okay, if it's a Gaussian random process, I have to figure out what order to do these things in. What's the past and the present? We'll usually take this to be the past. And we'll usually take this to be the future. Okay? Okay. But clearly there's an issue there because it's not symmetric. So so this is not general in this case. I have to be precise about what I mean by general, okay? But we'll be more precise later. This is really not going to be general because clearly if you pick an orientation to the scan, the class of distributions you can accurately model is going to be different than if you, say, scan this way, okay? So that's a problem, okay? But in any case, let's say we take the last, let's say we use these 1, 2, 3, these 4 pixels to predict that pixel, okay? What ends up happening is that, yeah, okay, it works, but it's a little weird. Let me see what I want to say beyond that. So this is, oh, I know. There's a lot more to be said, but the problem is you don't quite know enough yet for me to say it and it be useful. So let me just point out something which is more useful. Okay. Teaching. Okay. Okay, so this is 1D predictions. This is 2D, okay? And now what happens is that, okay, so this is the dependencies. Okay, what happens is that, and you know, some of this is going away or fading, you might say, because of all the tensor support, the software we have for tensors now, mostly driven by deep neural networks, have really driven the software development for tensor-based operations, okay? But when you had to vectorize this stuff, what ends up happening is you order the pixels. So you have an image like this, and you do a raster ordering of the pixels, okay? So what happens is that you take the first line and you put it here, right? And then you take the second line and you put it here. And then